In video 6, we figured out that language modeling is really just the prediction game. Guess the next word over and over at massive scale, and it works, right? The idea is sound. Here's the problem: we skipped over, and it's actually a big one. If the next word prediction is such a good idea, why didn't it work right away? Why did early models struggle for years before something finally clicked? And that's what this video is about. And by the end of it, the word transformer, which sounds sort of intimidating and technical and like it belongs in a research paper, is going to feel completely natural to you. You will understand why it had to be invented, because you'll see the problem it was invented to solve. So here's our question. The idea of predicting the next word has been around for decades, and we know that math works. The concept is solid, so what went wrong in the early attempts? Let me show you. The first serious language model did something that seems perfectly reasonable. They read text the same way you and I do. One word at a time, from left to right. The model would see the as a start of the sentence. If the start of the sentence is the, process it, pass some information forward, then see maybe cat, process that, pass more information forward, then next word would be sat, then on, and so on and so on, till it sees the entire sentence. Each word update a little chunk of memory that got handed over to the next word in the line. And you can actually watch this happen. You will see the model process each word in sequence. Watch the green bar, the green memory bar. They show how much model remembers about the beginning of each sentence as it moves forward. See what's happening? By the time we get to Matt, the memory of the has nearly vanished. That green bar is practically empty. Information doesn't survive. These models were called RNN, or recurrent neural network, and a fancier version called long short-term memory. The names sound impressive, but the fundamental approach was the same. Read one word at a time, pass information through a chain, hope that the important context survive to the end. Well, spoiler, it never did. Here is a sentence that makes the problem really concrete. I grew up in France, then imagine maybe three paragraph of unrelated stuff, and then comes therefore I speak fluent. You know the answer instantly, right? It's French. The word France at the beginning tells you everything you need to know about what language the person is speaking about. But an RNN reading this, by the time it reaches that blank, it processed hundreds of words since it saw France, and the memory of France has been overwritten, diluted, and effectively lost. And that's the first three fatal problem that we have. The forgetting problem. Memory decays with distance, so long range context just evaporates. Then comes the speed problem. Because word must be processed one at a time in order, you can't skip ahead or do anything in parallel, which make training painfully slow. And then bottleneck. The bottleneck problem. All the information about the entire sentence has to be squeezed through one tiny memory vector, which is like trying to summarize a novel by passing it through a keyhole. watch what's happening here to the model memory of France. As as it processes more and more word, see how it drops. By the time we need that information at the end of the sentence, it's basically gone. That's the core failure. The model forget exactly the thing it needs to remember. Here is a way to think about why this happens. Imagine you are playing a telephone game. You whisper a message to the person next to you. They whisper it to the person next to them, and so down the line. Watch the message travel through the chain. You can see the message here. The original message was I grew up in France and speak fluent French. By the person 4 or 5, it's already degraded to something vague. And by the end of the chain, the message is basically gone. That's exactly what happened inside a recurrent neural network. Information get whispered from word to word through a chain of hidden state. With each handoff, it degrades a little more. By the time you need the information from the beginning of a long sentence, it's been whispered through so many steps that the signal has turned to noise. So if that feels frustrating to watch, good, because it should. The telephone game is fundamentally broken way to preserve information over a long distance, and that's exactly the architecture that field was stuck with for years, which raises an obvious question: why do we force the model to read text in order? That's the question finally someone asked, and it changed everything. Because think about it, humans don't read that way. When we read a sentence and hit a word, let's suppose it, you don't really rely on some really rely on some degraded memory of what came 10 words ago. You just look back. You jump to the relevant word, check it, and move on. You compare distant part of a sentence instantly without any chain in between. But recurrent neural networks couldn't do that. They were locked into sequential processing, one word at a time, always forward, never looking back. So the radical idea was this: what if instead of forcing the model to read in order, we let it see everything at once? What if every word could look differently at every other word, with no chain and no bottleneck in between? The idea has a name. It's called attention. And the core idea is beautifully simple. Every word can look at every other word directly. No memory chain, no bottleneck. Just direct relationship between any pair of words in the sentence. And here's where it gets really fun. I've got a sentence here. The animal didn't cross the street because it was tired. And you can click on any word and see what happens, and see what it pays attention to, right? So let's suppose if I click it, right, and here's where it you can see that it attends to animal 65%, right? The attention is 65%. The model instantly look back at animal and figure out that it refers to the animal, not the street. No chain required, no degraded memory, just a direct connection between it and animal, no matter how far apart they are. Now let's suppose we click tired. See how it attends back to animal. The model knows who is tired. Now if we click, let's suppose, cross, it attends to street because that's what get crossed. And this is the whole breakthrough in one sentence. Instead of whispering information through a chain and hoping it survives, attention lets any word look directly at any other word. The information doesn't have to travel, the model just looks. Here is another way to think about what attention is doing. When you read a passage and someone asks you a question about it, you mentally highlight the words that matter for that specific question, and you dim everything else. You don't reread the whole thing. You zoom in on what's relevant. Look at these two examples. The same sentence, but different question. When a question is who is tired, the word animal, it, and tired lights up. But when the question is what didn't happen, the highlights shift to didn't, cross, and street. Same text, completely different highlighting, depending on what you are asking. That's exactly what attention does inside the model. It learns which words to highlight for which purpose, and the highlight pattern changes at every layer of the network. Early layer early layers actually might highlight a basic grammar relationship, while deeper layers highlight more abstract and semantic connections, and the model learn all of this automatically. Though the through the same training process we talked in video 5, predict the next word, compute the loss, and adjust the weight, is the same thing. So let's get a bit more specific about how this actually works. The mechanism is called self-attention, and every word in the input asks one question: which other word matter to me right now? And it answers that question through 4 steps. First, each word create a query. What am I looking for? Second, every word also create a key. What do I contain? Third, we compare each query against every key to get a score. How well do they match? And fourth, those scores determine how much attention each word pays to every other word. That's the entire mechanism. Queries, keys, score, attention. And the crucial thing is that this happens for every single word in the input. It happens at every layer of the network. So the first layer might learn simple relationship like which adjective goes with which noun. The next layer might learn more complex pattern like who did what to whom. And the deeper layer build even more abstract connections. The result is that context become global instead of local. In a recurrent neural network, a word can only see what was recently passed to it through a chain. With self-attention, every word has a direct access to every other word in the input. Nothing get lost, nothing get degraded, and nothing has to squeeze through a bottleneck. Let me put the old and the new approach side by side, so you can see just how dramatic shift this was. On the left, the recurrent neural networks and LSTMs had sequential processing, meaning they were slow, memory that decay with distance, we cannot parallelize well, so training would take forever, unstable gradient that makes the whole process fragile, and a limited context window because information doesn't survive the long chains. On the right, we have attention. which is parallel processing is possible, meaning it is fast, direct access to all contexts regardless of distance, massively parallelizable, so you can throw hundreds of GPU at it, stable training even at enormous scale, and long range relationship handled natively, because every word can see every other word. And this isn't an exaggeration. This single idea, attention, is the mechanism that made GPT possible, that made some initial models like BERT possible, that makes every modern large language model you have heard possible. Without attention, none of it works. And the best way to summarize this whole thing is, the model no longer remembers, it looks. That's it. The model no longer remember, it looks. Instead of trying to maintain a fading memory of what it's already read, it just looks back at the entire input whenever it needs to. That one shift from remembering to looking is what made modern AI possible. Here's one last mental model to tie it all together. Think of every word in a sentence as a person sitting around a conference table. Everyone can see everyone else. And each person gets to decide who they want to listen to most carefully. So let's suppose I click on it. Watch how animal lights up green. That's who it is listening to most. If I click tired, you will see it all turns towards animal. Click again cross, and it looks at didn't. Everyone at the table can hear everyone else. There is no chain, no whispering, no degraded signal, just direct communication. And compare this to the telephone game from earlier. In telephone game, the information had to pass through every person in sequence, degrading at each step. At conference table, everyone is in the same room, and any person can talk to any other person directly. That's the difference between recurrent neural network and attention. The telephone game versus conference tables. And once you see it that way, the transformer doesn't feel intimidating anymore. It feels like obvious solution to an obvious problem. All right, let's make sure this comes together, right? If everything clicked, you should be able to say one sentence and mean every word of it. Old language model failed because they processed words sequentially and forgot context. Attention fixed this by letting every word directly consider every other word. And that's it. Sequential processing caused forgetting, and attention solved it by replacing the chain with direct connection. If that feels obvious to you right now, and not impressive, not complicated, just straightforward and clear, then you have actually understood the most important architectural shift in the history of AI. And it's really is that simple. Now we have named attention and we have understood what it does and why it matters. But we haven't opened it up yet, right? We haven't looked at the actual mechanism, the queries, the keys, the values, how the scores get computed, and the whole thing fits together inside a transformer. That's video 8. Attention explained from scratch. No maths to panic about, just simple ideas. This is the heart of the transformer architecture, and we are going to go slow. We are going to go visual, and by the end of it, whole mechanism will feel so natural, same as conference table. I'll see you there.